Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the dry and atmospheric air and temperatures below the critical point. The gas phase of a substance is frequently referred to as a vapor. The term vapor implies to a gaseous state that is close to the saturation region of the substance, raising the possibility of condensation during a process. We have discussed mixtures of gases that are usually above their critical temperatures. Therefore, we were not concerned about any of the gases condensing during a process. Not having to deal with two phases greatly simplified the analysis. Then we are dealing with a gas-vapor mixture. However, the vapor may condense out of the mixture during a process, forming a two-phase mixture. This may complicate the analysis considerably. Therefore, a gas-vapor mixture needs to be treated differently from an ordinary gas mixture. Several gas-vapor mixtures are encountered in engineering. The air-water vapor mixture, which is the most commonly encountered in gas-vapor mixture in practice. Air is a mixture of nitrogen, oxygen, and small amounts of some other gases. Air in the atmosphere normally contains some water vapor and is referred to as atmospheric air. By contrast, air that contains no water vapor is called dry air. It is often convenient to treat air as a mixture of water vapor and dry air, since the composition of dry air remains relatively constant, but the amount of water vapor changes as a result of condensation and evaporation from oceans, lakes, rivers, showers, and even the human body. Although the amount of water vapor in the air is small, it plays a major role in human comfort. Therefore, it's an important consideration in air conditioning applications. The temperature of air in air conditioning applications ranges from about -10 to about 50 degrees centigrade. In this range, dry air can be treated as an ideal gas. It would also be very convenient to treat the water vapor in the air as an ideal gas, and you would probably be willing to sacrifice some accuracy for such convenience. Well, it turns out that we can have the convenience without much sacrifice. At 50 degrees centigrade, the saturation pressure of air is 12.3 kilopascal. At pressures below this value, water vapor can be treated as ideal gas with negligible error, even when it is a saturated vapor. Therefore, water vapor in air behaves as if it existed along and obeys the ideal gas relation. Then, the atmospheric air can be treated as an ideal gas mixture whose pressure is the sum of the partial pressure of dry air and that of water vapor. And we have this relation. The partial pressure of water vapor is usually referred to as the vapor pressure. It's the pressure water vapor would exert if it existed along at the temperature and volume of atmospheric air. If it is not intentionally compressed or vacuumed, the total pressure is the atmospheric pressure. We learned from this relation, the greater the partial pressure of water vapor, the more water vapor contained in the air. Based on the amount of vapor in the air, there are unsaturated and saturated atmospheric airs. Firstly, let's talk about the unsaturated atmospheric air. For the unsaturated atmospheric air, the vapor in the air is in the superheated state as shown in figures 7.1 and 7.2. For the unsaturated atmospheric air, the partial pressure of water vapor is lower than the saturated pressure corresponding to the temperature T. Unsaturated air has then the ability to absorb more moisture, that is, it can hold more water vapor. Secondly, let's talk about the saturated atmospheric air. For the saturated atmospheric air, the vapor in the air is in the saturated state as shown in figures 7.1 and 7.2. Saturated air has no longer the ability to absorb moisture. If water vapor is added, water will condense immediately. Okay, that's all for this task. Thank you very much and see you next time.